So section 5, here we go, is about Newton's second law. Do you remember what Newton's first law was?
No, don't say that, Cole. You're gonna make it angry. You're not gonna like him when he's angry.
Well, at least we're honest.
What was it? How did we say it?
Oh, yeah. If an object is at rest, it will remain at rest. If an object is moving.
What? If an object is at rest, it will stay at rest. If an object is moving, what?
It will stay moving unless an force is acted upon.
Okay, it will stay moving unless another force is acted on. Okay, so here is Newton's second law. Newton's second law reads like this. Acceleration equals F over m, force divided by mass. We actually wrote this. I wrote this in section 4. But we weren't 100% sure if this was actually it, if there was maybe another constant being multiplied on or something like that. But it is actually this. Acceleration equals force divided by mass. And the reason that we like to write it in this form is it summarizes everything that we know about the relationship between acceleration and force and mass. We see the direct proportion relationship between acceleration and force, and we see the inversely proportional relationship between acceleration and mass when it's written in this form. Most of the time, like on TV and TV shows, or in other books or whatever, you see this form. If we multiply both sides by mass, you would see F equals ma. Yeah, that's Newton's second law, right? Everybody knows that one. But it doesn't, so force is still a vector and acceleration is still a vector, so we need arrows over the top of those. Everybody recognizes that one because F equals ma is what everybody knows, right? But sure, but that doesn't really get at the relationship between force and mass and acceleration. They're actually better written like this because we get at the relationship between those two ideas, okay? So, if we double the force, the acceleration will also double. If we triple the mass, the acceleration will only be 1/3 as much as it was before. Also, the force and acceleration are vectors. The force applied results in acceleration in the same direction. That's very important. If I apply a force in a direction, the acceleration will be in that direction as well. Finally, the force applied can actually be the vector sum of all the forces acting on an object. In other words, the acceleration that the object will undergo will be in the direction of the net force that's acting on the object. So maybe I have an object and gravity is acting on it, so there's a weight vector. We have a push that's acting on it, we have a pull that's acting on it, maybe at an angle, so we break that angle into components. Maybe there's some sort of tension that's going on. Maybe there's all kinds of these vectors, forces that are acting on this object. We find a net force that's acting on the object, and that net force tells us which way the object is accelerating, okay? If it actually ends up moving at all. So this formula right here, acceleration equals F net divided by m, is the law that we want to know for sure. So obviously we can rewrite Newton's second law in this form, as I already mentioned. This is the one that everybody knows. But we're going to be smarter than that. We're going to be using A equals F over m. So because otherwise it's easy to forget the relationships between force, mass, and acceleration. Very important. That's why I keep saying it. All right, finally we're going to learn about the unit of force. Since F net equals mass times acceleration, the units of force must be the unit of mass, which is a kilogram. Our SI unit of force is kilogram, multiplied by the units of acceleration, which we've been using for months now, meters per second squared. So that means the unit of force is a kilogram times meters per second squared, and that's a lot to be needing to write. So what happened was we decided to use a standard unit for force. So we didn't have to write kilograms times meters per second squared all the time. And that standard unit of force is called a Newton, probably named after Sir Isaac Newton, but we won't get into that. So 1 Newton is our standard unit of force, and it is 1 kilogram times meters per second squared. Easier to say as 1 kilogram meter per second squared, okay? So when you are working with mass times acceleration, you'll want to have kilograms and meters per second squared. Unit conversions until you have that, and then when you multiply stuff together, you should wind up with those units multiplied out so that you have newtons in the end. The unit of force in the English system is the pound, and that's where things get confusing in the English system, because pounds could mean force, meaning weight, but it could mean mass also. So it's very confusing. So that's why we don't like to use it. So we have 1 pound of force would be 1 lb, and that is 4.45 newtons. So this conversion right here is kind of a big one for us. 1 pound is 4.45 newtons. Don't confuse pounds to mean mass. Pounds are a weight, which is a force. Newtons are a weight, which is a force. Alright, so we have some typical things that we use in our daily lives here that will tell us our approximate magnitude in newtons. Weight of a U.S. nickel, 0.05 newtons. Weight of a quarter cup of sugar, 0.5 newtons. Weight of a 1 pound object, this is approximate. Remember, I just told you 1 pound up here is 4.45 newtons, so these are nice approximations only. Weight of a 1 pound object, 5 newtons. Weight of a typical house cat, unless you have a fat cat, it would be 50 newtons. Weight of a 110 pound person would be 500 newtons. Propulsion force of a car, your standard car, not your Bugatti, would be 5,000 newtons. Thrust force of a small jet engine would be 50,000 newtons. This would not be a fighter jet, this would be more like a passenger jet. And the pulling force of a locomotive is pretty impressive at 500,000 newtons. So each one of these things is just multiplied by an order of magnitude, which would be, an order of magnitude, by the way, is 10. So each one is multiplied by 10. Kind of interesting little chart here. All right, so racing down the runway. All right, so a Boeing 737, which is a typical small short-range jet with a mass of 51,000 kilograms, sits at rest at the start of a runway. The pilot turns on the pair of jet engines to full throttle, and the thrust accelerates the plane down the runway. After traveling 940 meters, the plane reaches its takeoff speed of 70 meters per second, which is how much in miles per hour, so we can get an idea? 140, add a little, 150-ish, maybe a little more than that, 160, we don't know exactly. Leaves the ground. What is the thrust of each engine? How many engines does it have? It has 2. We want the thrust of each. Okay, so we got to keep that one in mind. Okay, Boeing 737, we don't really care what jet it is, doesn't matter. Mass of 51,000 kilograms, do we care about that? Okay, we probably want to write that down then. M equals 51,000 kg. And we're just making our inventory of stuff that we know. What else do we know? We do? No, we don't. Delta X. Do we know delta X?
940.
Okay. Should I write it as delta X or should I write it as X sub I and X sub F?
Delta.
Okay, delta X equals 940 meters. Let's write that one not as delta V. V sub I is what? 0 meters per second. And V sub F? 70 meters per second. Okay, just want to like writing that one out because I want you guys to always understand that we're at rest, which means 0 meters per second.
So we can calculate its acceleration now using what we have?
We can calculate its acceleration. Now, what formula are we likely to use here if we're talking about thrust? Thrust is a what? Thrust is a force. So we're likely to use our Newton's second law, our force equation, okay? Now, because we're looking for thrust, we probably want that equation solved for F, our force. So we're going to be using F equals ma, that version, okay? But we're going to have to find acceleration. Now we're going to need a formula that will allow us to find that.
Equals, acceleration equals, mass, or, velocity over distance. Or is it distance over velocity? Or distance over time?
Oh, we don't know anything about time though.
Dang.
So since we don't know anything about time, we're going to need some other equation that would involve the stuff that we do have, which is delta x, and v sub I and v sub f.
So it's v sub f, so v sub x equals v sub x meter, and the plus v to the next delta x.
Yes, that's the one. Okay, so v f squared equals v I squared plus 2a delta x. This is all in one direction, so I have no problem not using vxf and vxi and 2ax. All in one direction, I can drop those subscripts. Okay, so what do we know? What do we know? Velocity initial is 0. Anything else?
No.
Okay, what am I looking for here?
Hey,
I'm looking for acceleration, so I'm going to solve for acceleration. How will I do that?
divide by 2 delta x.
Divided by 2 delta x. So I have v sub f, what am I doing here? V sub f squared divided by 2 delta x equals a. Now I know everything, so v sub f is 70 meters per second squared. Not squared, it's just meters per second. That is squared. There we go.
Divided by
2
times 940 meters.
delta x is 940 meters.
Equals,
Okay, now let's look at the units on this. We have 70 meters per second. That's being squared. That's going to be meters squared per second squared. We're going to divide by meters. Then the meters squared would become just meters, and we have meters per second squared. So the units work out. We just need an answer. 2.606 meters per second squared. Okay. Now, what do we do?
Now we use our force.
Now we can use the force equation up there to give us the force, the thrust.
So we have F equals the mass, which is
51,000 kilograms.
times the calculated answer, 2.6.
Meters per second squared. The calculator's answer, though, use that. What do we get for the force?
56,000. Why didn't you have it on the
Okay. 66,000 newtons is the answer.
Yep.
Yay.
But it's not. That's not what your calculator gave you. What does your calculator give you?
Hold on. No, it's not right. You're right.
Yeah, 51,000 times 2 is over 100 already. 132, 9 something? 26 newtons. Now, this is the thrust total.
Oh, we got to divide by 2.
It's the thrust of each engine that we're looking for. So now we're going to divide by 2 to get the thrust of one engine, and this is where 66,000 is the answer, okay? So divide this answer by 2, what do we get? So then if we do significant figures on 66,400 blah blah blah, what do we have?
66.
Yeah, it would be 66,000.
About that first answer on the next.
Maybe you did that on purpose.
All right, so there you go. Okay, so this is the last problem of this section. Three forces act on an object. In which direction Does the object accelerate?
I can mark it in like that.
What do you think? You think it's D? Any other answers?
D.
Two votes for D? That's it?
I'm missing
You just making stuff up?
No, because I think that, D is it would be more down. Not-
More down?
It would be more like this instead of, or like.
So
instead of
C
this,
is
like-
showing straight down is the problem, right?
Yeah, well, I'd say it's like neither.
We have this vector F2 that's pointing us to the left, which means we will move to the left because there's nothing counteracting that, okay? So our answer choice has to have something to the left. So that's not A, that's not C. Now, we have to assume in the picture that they are intentionally making these vectors the correct length. F1 definitely looks shorter than F3, so when I add those together, I will have a result that is in which direction? Down. So that means when I add all these vectors together, I have a result that is down, and I have a result that is somewhat left, which means my resultant vector will be in that direction when I add them together, okay? So the only answer that works is D. That's how you do that. The net force is the sum total of all of the vectors. Because we didn't have a component to the right to add with the F2 to get it to go away, it must be left in some way and then down in some way. That's how you do those.